Hello, and welcome to this presentation on curve sketching. This presentation does assume you've seen a previous presentation relating to a recap of standard curves. Within this presentation, we're going to look at some simple transformations. So from the graph of y is equal to the function of x, it's possible to determine the graphs of other functions which are transformations of the y is equal to the function of x. So knowing the graph of y is equal to the function of x helps us sketch the other graphs. So there are 6 types of transformation that we are going to consider. Type 1. Y is equal to a multiplied by the function of x. This has the effect of factoring the curve by a in the y-axis. Type 2. Y is equal to the function of x plus a. This has the effect of shifting the curve by a in the y-axis. Type 3, y is equal to the function of, in brackets, x plus a. This has the effect of shifting the curve by a in the x-axis. Type 4, y is equal to function of, in brackets, a multiplied by x. This factors the curve by a in the x-axis. Type 5, y is equal to negative function of x. This has the effect of reflecting the curve about the x-axis. And finally, type 6, y is equal to function in brackets negative x. This has the effect of reflecting the curve about the y-axis. So let's now consider the 6 types of transformation. So type 1, scaling the graph in the y direction. The y is equal to a multiplied by the function of x. For each point, x1, y1, there exists a point x1, ay1 on the graph of y equals a multiplied by a function of x. The graph of a multiplied by the function of x is obtained by stretching the y is equal to the function of x in the y-axis by the scale factor of a, the constant a. So for example, if function of x is equal to x plus 3, then y is equal to a times the function of x, in this case 2 times the function of x, becomes y is equal to 2 multiplied by x plus 3. So as x plus 3 is a linear equation, this has the effect of factoring the gradient and the intercept by a. So considering the equation y equals x plus 3, the linear line, we plot this line passing through 3 on the y-axis. If we now consider the equation y is equal to the x plus 3 factored by 2, we plot this line here, where the gradient is now double and the intercept is now double. So the gradient of the first line plotted here is 1, so 1 in a 1, and the intercept is 3. The gradient of the second line plotted here is 2 in 1, so double the gradient, and the intercept is 6. If we consider the function of x equal to sine x, then y is equal to 3 multiplied by the function x becomes y is equal to 3 multiplied by sine x. In this case, we will see that the amplitude is factored by the constant a. So on our graph, this is the sine x curve plotted here for us in the yellow. And if we consider 3 multiplied by the sine x, we will plot this curve where the amplitude is now 3 times that of the sine x curve. So the amplitude of the sine x curve is 1, and the amplitude of the 3 sine x curve is 3. Type 2, this is where the curve is now shifted in the y direction. We have the form y is equal to the function of x plus a. So a graph of the y is equal to function x is translated by a units along the x-axis to obtain the y is equal to the function x plus a. So for example, if the function of x is equal to 2x, then y is equal to function x plus 1, where a is 1, becomes y is equal to 2x plus 1. So on our graph here, if we plot the line y is equal to 2x, we will plot this line. It would have a gradient of 2, and it would pass through 0 on the origin because there's no c term. If we now plot the y is equal to 2x plus 1 equation, we'll plot this line here, which is 1 higher than the y is equal to 2x curve. So in other words, the y is equal to 2x crosses through 0, 0. The y is equal to x plus 1 crosses through 0, 1 on the y-axis. If we consider a function of x is equal to cos x, then y is equal to the function x plus 3 would be y is equal to cos x plus 3. If we plot the cos x curve, we would plot this curve here. This is the cosine curve. If we plot the curve cos x plus 3, we will plot the same shape of curve as the cos x curve, but it's now shifted by 3 on the y-axis. So in other words, the cos x curve cuts the y-axis at 1, and the cos x plus 3 cuts the y-axis at 4. In other words, 3 added to the cos x curve. If we consider the function of x equals 2x squared, then y is equal to the function of x minus 10 becomes y is equal to 2x squared minus 10. If we plot the y is equal to 2x squared curve, that's a quadratic shape, parabolic shape here, passes through 0, 0 the origin. If we plot the y is equal to 2x squared minus 10 curve, then we plot the same shape, but it now crosses the y-axis at negative 10. So the y is equal to 2x curve crosses here at 0, 0. The y is equal to 2x squared minus 10 crosses the y-axis at negative 10. Type 3 transformation, this is going to shift the curve in the x direction. So this is y is equal to function of, in brackets, x plus a. So a graph of y is equal to function of, in brackets, x plus a, is translated by a units along the x-axis to obtain y is equal function of, in brackets, x plus a. If the a is greater than 0, then the y is equal to the function of x moves in the negative x direction, i.e. to the left. If the a is less than 0, then y is equal to the function of x moves in the positive x direction, i.e. to the right. Some quadratic curves shown on the right. So considering our y is equal to x squared curve, then it would be this curve here, going through 0, 0. Y is equal to x squared, quadratic curve. If we plot the y is equal to, in brackets, x plus 1 all squared, we would plot this curve here, where the curve has shifted to the left by 1 unit. If we plot the curve y is equal to x minus 2 all squared, we will plot this curve here, where the curve is now shifted to the right by 2. So our original quadratic curve has its vertex at 0, 0. That's the y is equal to x squared curve. If we now plot the y is equal to x plus 1 all squared, that has its vertex now at negative 1 on the x-axis. And if we plot the y is equal to x minus 2 all squared, that has the vertex at positive 2 on the x-axis. So a type 3 transformation shifts the curve either along the x-axis to the right or to the left. Further type 3 transformations, we have a function of t this time is equal to cos of t. So y is equal to the function of t plus 45 degrees would become y is equal to cos of, in brackets, t plus 45 degrees. So plotting the basic cos t curve, we would get this shape, on our diagram. It's the basic cos function. If we plot the cos t plus 45 degree curve, we would get this shape on our diagram. What we notice is that we have a shift of 45 degrees along the x-axis. So looking at the maximum amplitudes, we can see that on the cos t curve, the maximum amplitude occurs at 360 degrees. And looking at the maximum amplitude on the cos t plus 45 degrees, the maximum amplitude occurs at 315 degrees, i.e. 45 degrees before. And this is actually called a leading waveform. Another example here, consider the function of a is equal to sine of a, then y is equal to the function of a minus 60 degrees becomes y is equal to sine of a minus 60 degrees. If we plot the basic sine curve on our graph, we would get this shape here. And if we plot the sine a minus 60 degrees, we would get this shape shown here. On inspection of the graph, what we notice is the basic sine curve peaks here, maximum amplitude here, and that's at 90 degrees. And looking at the sine a minus 60 degree curve, that peaks here, and that's at 150 degrees on the x-axis. In other words, 60 degrees later. This is called a lagging waveform. So type 4 transformation. Here the curve is scaled in the x direction by a factor. Format of the equation is y is equal to function of, in brackets, a multiplied by x. So a graph of y is equal to function of ax is found by stretching the y is equal to function of x equation in the x direction by a scale factor of 1 divided by the constant a. So consider an example of function of x is equal to x plus 1 all squared. If we now let a is equal to a half, then y is equal to function of a multiplied by x becomes y is equal to x divided by 2, that's the a of a half multiplied by x, plus 1 all squared. So what we will notice in the graph below is that the original equation, function of x equals x plus 1 all squared, will be factored by 2 in the x direction. If we now plot the original function of x equation, y is equal to x plus 1 all squared, we plot this shape here, which is a parabolic curve based on the quadratic equation given. If we now plot the y is equal to x divided by 2 plus 1 all squared, so the a is equal to a half in this case, we plot this shape as our parabolic curve. What we now notice is that the original curve, the yellow curve, is being factored by 2 in the x direction to produce the green curve. In other words, the scale factor is 1 upon a, and 1 upon a is 1 upon a half in this particular case, so 1 divided by a half is 2. So the original curve, the yellow curve, had the vertex at negative 1. What we notice with the green curve, our factored curve, the vertex is moved to negative 2, so it's a factor of 2. Also on the original curve, when x is equal to 1, the value of y is equal to 4. On the curve with the a is equal to a half, the value of 4 in the y would occur when x is equal to 2. So again we have a stretching in the x direction by the factor of 2 in this case. If we now consider the curve y is equal to function of a, and that function of a is sine of a in this case, sine of 1a. If we now let the a is equal to 2, then the y is equal to function of a times a here, where little a is this factor and a is the angle, becomes y is equal to sine of 2 times a. If we now plot sine of a, the original sine curve, between 0 and 360 degrees, we will plot this shape here, a conventional curve. If we now consider the sine of 2a, what we will find is the equation will be stretched in the x direction by scaling factor of a half, 1 upon 2. So the equation sine 2a will actually form this shape here. So between 0 and 180 degrees we will get a full sine curve, and then between 180 degrees and 360 degrees we get a second sine curve. So we scaled by a half in the x direction because the a is equal to 2. If we again consider the function of a curve equal to sine a, but this time the factor a is a half, then our y is equal to the function of the a times a becomes y is equal to sine of a upon 2, in other words a half of the angle a. Now the scaling factor is 1 upon a half again. 1 upon a half is actually 2. So what we're going to do now is scale the equation y is equal to sine of a by 2 in the x direction. If we now plot the sine of a half a curve between 0 and 360, we find we plot just half of a sine curve because we have a scaling factor of 2. In other words, we're stretching the y is equal to sine a curve in the x direction by a factor of 2. So to get the full sine curve for the y is equal to sine half a, we would need to plot the curve between 0 and 720 degrees. So in all these examples, what we're finding in the y is equal to the function of a multiplied by x, the a is a scaling factor in the x direction. It either extends or contracts the equation in that direction. The type 5 transformation, this is where the curve is reflected about the x-axis. So y is equal to the negative function of x. The graph of y is equal to a negative function of x is obtained by reflecting the graph y is equal to function of x about the x-axis. Examples here, function of x is equal to e to the x, then y is equal to negative function of x will be y is equal to negative e to the x. You could think of that, if you like, as being y is equal to negative 1 multiplied by e to the x. So if we plot the y is equal to e to the x curve, we would get this shape, and if we plot the y is equal to negative e to the x curve, we would get this shape. In other words, a mirror image about the horizontal x-axis. Another example, if the function of x is equal to log to the base 10 of x, the common logarithm, then y is equal to negative function of x becomes y is equal to negative log to the base 10 of x. Again, you could think of that, if you like, as y is equal to negative 1 multiplied by log to the base 10 of x. So plotting log to the base 10 of x, the common logarithm, we would get this shape here on our graph. And if we plot the equation y is equal to negative log of x, we would get this shape. Again, a mirror image about the x-axis. Type 5 transformation continued. Another example, function of x is equal to x squared plus 1, it's a quadratic equation. Then y is equal to a negative function of x becomes y is equal to negative, in brackets, the x squared plus 1. So if we plot the y is equal to x squared plus 1 curve, we get this shape passing through the vertical axis at 1. And if we plot the y is equal to negative x squared plus 1, we get this shape passing through negative 1 on the vertical axis, and again the mirror image about the x-axis. Final example here, if we have the function of x equal to x cubed, then y is equal to negative function x becomes y is equal to negative x cubed. So plotting the y is equal to x cubed function, we will get this shape here, or cubic, and then plotting the y is equal to the negative x cubed, we will have this shape here. And again, mirror image about the x-axis. Further type 5 examples, look at sine x first of all. Here is the sine x curve plotted between 0 and 360 degrees. If we consider the negative sine x function, we will plot this shape here. As you can see, it's against the mirror image of the sine curve about the x-axis, and it applies whether we're looking to the left or the right of the vertical axis here. Likewise, if we consider the cos x function, this is the cos x curve plotted between 0 and 360 degrees. And if we consider the negative cos x function, then we plot the mirror image again about the x-axis. So this is negative cos x here. So that applies for both positive and negative values of x. And finally, type 6 transformation. This is the curve reflected about the y-axis. So y is equal to function of, in brackets, negative x. So the graph of y is equal to function of negative x in brackets is obtained by reflecting the graph y is equal to function of x about the y-axis. For examples, function of x is equal to x squared, then y is equal to the function of negative x becomes y is equal to, in brackets, negative x or squared, which is x squared. So in this particular case, plotting the y is equal to x squared is the same as plotting the y is equal to the negative x all squared. If we now consider function of x is equal to x cubed, then y is equal to function of, in brackets, negative x becomes y is equal to, in brackets, negative x cubed. So that would be negative x cubed, because a negative x multiplied by a negative x is a positive x squared, and multiplied by a negative x is a negative x cubed. That's like having negative 1 multiplied by the x cubed curve. If we plot the y is equal to x cubed curve, we will get this shape, passing through 0, 0 on the origin. And if we plot the y is equal to negative x cubed, we will plot this shape here, in other words, reflecting about the y-axis. Type 6 transformation continued here. Here's the curve y is equal to e to the positive x. That would plot like this. And if we consider the y is equal to e to the negative x curve, that would plot like this. And again, we can see it's a mirror image about the y-axis. Type 6 transformation continued. Don't forget the reflecting about the y-axis here. So if we plot a sine x curve between 0 and 360 degrees, we will get this shape. If we plot a sine x curve between 0 and negative 360 degrees, we would get this shape. If we now plot the sine negative x curve, then we will get this shape, a reflection about the y-axis from 0 to 360 degrees. And if we plot from 0 to negative 360 degrees, we would get this shape, again the reflection about the y-axis. If we now plot a cos x function between 0 and 360 degrees, we get this shape, our conventional cosine waveform. And if we plot the cos x waveform between 0 and negative 360 degrees, we get this shape to the left hand side of the vertical axis. If we now plot the function cos of negative x, we find we actually get exactly the same shape as a cos x waveform between 0 and 360 degrees, and the same shape between 0 and negative 360 degrees. So we still have our reflection about the y-axis, but we have the same shape reflected. So for your reference, if you compare type 5 solutions with type 6 solutions for the sine wave, we find that a negative sine x function plots the same as a sine of a negative x function. If you compare the cosine waveform, we find that a negative cos x function does not plot the same as a cos of a negative x function. Example 1. We're asked to sketch the graph of y is equal to x plus 4 all squared. So y is equal to x plus 4 squared is a type 3 graph of the form y is equal to function of x plus a, where a is equal to 4. And if we plot the y is equal to x squared curve, we would plot this shape with the vertex passing through the 0, 0 position, parabolic shape. If we now plot the y is equal to x plus 4 all squared equation, we find that the vertex shifts to the left by 4 units, so the vertex crosses at negative 4. Example 2. We're asked to sketch the curve y is equal to x cubed minus 10. So y is equal to x cubed minus 10 is a type 2 transformation of the form y is equal to function of x plus a, where a in this case is negative 10. So as a is equal to negative 10, the curve y is equal to x cubed is translated negative 10 units down the y-axis. I suggest you stop the presentation for a moment and just sketch the curve y is equal to x cubed and y is equal to x cubed minus 10. Solution shown on the following slide. Example 2, here's a sketch of y is equal to x cubed minus 10. So if we plot the y is equal to x cubed curve, this is what we would get. Passes through 0, 0, this shape here. And if we plot the y is equal to x cubed minus 10, we'll plot this curve here, which is 10 units below the y is equal to x cubed curve on the y-axis. So the y is equal to x cubed curve is crossing through 0, 0 here, and the y is equal to x cubed minus 10 curve is passing through the negative 10 on the y-axis. Example 3. We're asked to sketch the graph y is equal to 4 minus, in brackets, x minus 2 all cubed. The graph given in example 3 is quite complex to plot, but we can consider it to be split down into several standard curves, standard transformations, and we summate the effect of these various transformations, and we can build up the curve as shown below. So step 1 here, our y's function of x is y is equal to x cubed. If we plot the y is equal to x cubed on our graph, we get this shape here. Example 3, we're asked to sketch the graph of y is equal to 4 minus, in brackets, x minus 2 all cubed. We're going to break this down into 3 separate transformations. So we're going to use a type 3 transformation of the form y is equal to function of, in brackets, x plus a type 5 transformation of y is equal to negative function of x, and a type 2 transformation of y is equal to function of x plus a. I'd encourage you to stop the presentation now and try and attempt these 3 types of transformations shown on the slide to develop the curve y is equal to 4 minus x minus 2 all cubed. Here is solution to example 3. We were asked to sketch the graph of y is equal to 4 minus, in brackets, x minus 2 all cubed. So in step 1 of this solution, y equals function of x, we start with y is equal to x cubed. This is plotted on the curve on the right hand side. Step 2 is a type 3 transformation of the form y is equals function of, in brackets, x plus a. So in our case, that would be y is equal to x minus 2 all cubed from the information in the question. So a type 3 transformation shifts the equation to the left or to the right. If it's a positive a, it shifts it to the left, and if it's a negative a, it shifts it to the right. In our case, the a is negative 2, so the equation y equals x cubed is shift 2 increments to the right in this particular instance. So in step 1 above, in the original equation y equals function of x, the equation y equals x cubed passes through the origin 0, 0. But in step 2, under a type 3 transformation, the curve is now shifted 2 increments to the right. So the 0, 0 in step 1 has now become 2, 0 in step 2. Step 3 is a type 5 transformation of y is equal to negative function of x. So now we have y is equal to negative the x minus 2 all cubed. A type 5 transformation mirrors the curve about the x-axis, so mirroring the curve shown in step 2, here in step 3 it will look like this. And finally in step 4 we've got a type 2 transformation of the form y equals function of x plus a. This shifts the curve in the y direction. So in our case, we've got y is equal to the negative x minus 2 all cubed in brackets plus the 4. So the a in this case is 4, so that means the entire curve shown in step 3 above is now shifted 4 increments in the vertical, as shown here. So if we look at the curve in step 3, we can see the intercept with the y-axis is at positive 8, and reviewing the curve in step 4, the intercept with the y-axis is positive 12. In other words, there is a shift of positive 4 in the y direction as we move from step 3 to step 4 and introduce a type 2 transformation. And that's the final transformation for the equation y is equal to 4 minus in brackets x minus 2 all cubed. Example 4, we're asked to sketch the graph y is equal to 2 plus 3 cos 2x. So again, the graph of y is equal to 2 plus 3 multiplied by the cos of 2x can be split into several standard curves or transformations. So we're starting off with y is equal to the function of x, in this case the y is equal to cos x. This is a plot of y is equal to cos x between 0 and 360 degrees. Example 4 continued. We're asked to sketch the graph y is equal to 2 plus 3 cos 2x. Now in this case we're going to have a type 4 transformation, so that's a y is equal to the function of ax. So y is equal to cos 2x, where the a is equal to 2. That's our first transformation to think about. And we've got a type 1 transformation, the y is equal to a multiplied by the function of x. So in this case that's y is equal to the 3 multiplied by the cos 2x. A is 3 for the type 1 transformation. And finally the type 2 transformation, y is equal to the function of x plus a. So that's the y is equal to the 2 plus the 3 multiplied by the cos 2x, where a is equal to 2. I would again encourage you to stop the presentation and try and sketch transformations on the basic cos x curve. Solutions are shown on the following slide. Example 4 solution, we're asked to sketch the graph y is equal to 2 plus 3 cos 2x. We're given the original function of x, in this case it's y is equal to cos x, and we plotted that on our graph between 0 and 360 degrees. Type 4 transformation, here we got y is equal to function of in brackets a multiplied by x. Our y now will be cos of 2x, where a is equal to 2. That has the effect of doubling the frequency, so now we get two cosine waveforms in 0 to 360 degrees, or in other words we get a full waveform in a period of 0 to 180 degrees. Type 1 transformation, y is equal to a multiplied by the function of x. So now that's y is equal to 3 multiplied by the cos of 2x, where the a is equal to 3. That has the effect of expanding the equation in the y direction, so the amplitude now has been factored by 3. So now we go up and down to 3, up to 3 and down to minus 3. And that's our waveform there with the type 1 transformation. And finally we've got a type 2 transformation, that's y is equal to the function of x plus a. So that's y in this case equal to 2 plus the 3 multiplied by the cos of 2x. So a is 2 for the type 2 transformation. That has the effect of shifting the whole waveform 2 increments in the y direction. So instead of starting from 3 and going down to an amplitude of negative 3, as we did in the type 1 transformation, now we're going to start from 5 and go down to negative 1. So our final solution will look like this for the final waveform of 2 plus 3 multiplied by the cos of 2x. Okay, I'm going to leave you with some tutorial questions now. You're asked to sketch the following graphs indicating principal points such as intercepts with the y-axis or vertices. So question 1 and question 2 start with the y is equal to x function and use your transformations from there to develop the equation stated. Questions 3, 4 and 5 I suggest start with the y is equal to x squared function and using transformations develop the equations as required. Question 6 contains an x and an x squared function, so I would suggest you sketch those first of all and see how that develops the equation required, the y is equal to x minus the x squared. Question 7, start with a y is equal to x cubed function. Question 8, start with a y is equal to cos x function and using transformations develop to the equation required. Question 9, start with a sin x function and again using various transformations develop to the equation required. And finally, question 10, start with a y is equal to ln x function. Tutorial questions continued. It's question 11. With reference to the 40 graphs shown on the next slide, we've got to find the graphs of the following 20 sub-questions here, the heading of question 11. They relate to the graphs on here. There's 40 versions there, different graphs there, and we've got to choose which graph fits the equations, 20 equations to deal with here. I would encourage you to stop the video and attempt questions 1 through to 11 and the sub-questions shown here before reviewing the answers on the following slides. There are selected solutions also included. Here are the answers. Question 1. We start with y is equal to x. We apply a type 1 transformation. We apply a type 2 transformation. In question 2, we start with the y is equal to x function again, and we apply transformation types 5, 1, and 2. Question 3, we start with the y is equal to x squared function, and we apply the type 2 transformation. I suggest you think through those transformations for yourself. And for reference with question 2, you could apply the type 1 transformation first, then the type 5, and then the type 2 transformation. Answers to questions 4, 5 and 6 are shown here in square brackets at the bottom. I suggest you stop the presentation and think through those transformation types. Question 6, start with the y is equal to x squared function and apply the type 5 transformation, which reflects the function about the x-axis. Then look at the effect of the y is equal to x function on the y is equal to negative x squared function. You'll see we get this shape here, slightly skewed shape for the final solution of y is equal to x minus x squared. And here are the answers for question 7, question 8, question 9 and question 10. Here are some selected solutions to the tutorial questions. This is question 1 solution, showing the transformation required. Solution to question 3 here. Solution to question 5 shown here. Solution to question 6 shown on this slide. Solution to question 8 shown on this slide. Here's a bibliography which I would strongly encourage you to review. It's very good textbooks here specifically written for technician engineers. And I hope this presentation has been of help to you, and thank you for viewing.